Cancer is a devastating disease that causes 1 in every 4 deaths in the United States. To treat cancer, bioengineers have imagined a variety of nanoparticles that can potentially deliver therapies directly to tumors. The challenge is to get these nanoparticles to all the cancer cells they need to treat in sufficient amounts and without causing side effects on healthy tissue. Nanoparticles are 1 to 1,000 nanometers in diameter. That's between 100 to 100,000 times smaller than the thickness of a human hair. They come in many sizes and shapes and can be charged or neutral. Their core can be made of a wide variety of materials which are energy receptive, biological, or synthetic. They can also be coated with specialized molecules that allow them to interact with their environment or loaded with therapies that are released in a controlled fashion. Tumors grow when cells accumulate several mutations that allow them to replicate uncontrollably. To feed this growth, tumors stimulate recruitment of vessels that are typically badly distributed and abnormally small, tortuous, and leaky. These leaky vessels pump liquid into the tumor, thereby increasing its pressure. As the tumor grows, proliferating cells start compressing the lymphatic system, which is supposed to pump liquid out of the tumor. Eventually, the lymphatic system collapses and the pressure builds until it is uniformly high, which means that there's no flow. Anything that needs to move through the tumor, whether it's oxygen, nutrients, or nanoparticles, must slowly diffuse. Towards the edge of the tumor, however, where the lymphatics and vessels are restored, pressure decreases, leading to outwards flow from the tumor. This can make it difficult for nanoparticles that are in tissue surrounding the tumor to enter. One way for nanoparticles to reach the inside of the tumor is through the leaky vessels. This challenging tumor environment arises very early on in the development of cancer. Whereas normal vessels usually do not let nanoparticles escape, tumor vessels have pores that are several hundred nanometers large. Nanoparticles are able to leak out of these vessels into the tumor, where they usually stay due to the high-pressure environment. How well nanoparticles leak out of vessels depends on many factors. Making sure that nanoparticles stay in circulation as long as possible will increase their probability of escaping from the bloodstream. To camouflage nanoparticles from the immune system and keep them in circulation, engineers often coat them with specialized molecules such as PEG that make them invisible. After extravasation, the nanoparticles are free to diffuse throughout the tissue. Releasing a drug or heat can be sufficient to impact the tumor. There are situations, however, where it makes sense to deliver drugs specifically to cancer cells, thereby sparing surrounding healthy tissue. This can be done by decorating nanoparticles with targeting moieties that allow them to bind to receptors overexpressed on the surface of cancer cells or to elements in their environment. Not only does targeting improve the ability of nanoparticles to act only on cells for which they were designed, it can also potentially activate receptor uptake pathways, leading to the delivery of nanoparticles directly to the inside of the cell, which is useful for cargoes such as gene therapies. Targeting, however, poses several challenges since it affects where nanoparticles distribute within the tumor tissue. Understanding how nanoparticles distribute is critical to effectively treat all cells in the tumor. For example, particles that bind strongly and that are big and slow will tend to accumulate in the first cells they encounter after extravasation. Such accumulation is called a binding site barrier. Particles that are fast or that don't bind very strongly to their environment will be able to penetrate deeper into the tissue. Overall, nanoparticle transport to tumors relies on improved circulation time, extravasation, accumulation, and tissue distribution.